In the last segment, we looked at a specific case of the decomposition of hydrogen peroxide to form water and oxygen, and looked at how to use some data found in your textbook that was collected experimentally in order to determine the rate law. In this segment, we're now going to look at how to generally think about rate laws and how to understand them. To do that, I'm going to put in an arbitrary example reaction here. That reaction is going to be one that involves 2 moles of A plus 1 mole of B going to form some product P. One of the most common challenges to putting together rate laws is thinking about how these individual components interact or come together. So, to start out, we want to write these actual rates. Now, rate laws, or excuse me, rates themselves, rates are always positive. Rates will typically be reported in units like molarity per second or bar per second. That is, changes in concentration or pressure, some amount, over time. But for that number to be positive and related to the concentration of these quantities, we're going to need some negative numbers. That's because if we look at our concentration of each of our components over time, we would expect that our amount of A should be decreasing quite rapidly. Our amount of B, assuming that we had half as much, might be declining as well. And simultaneously, our amount of product would be increasing. If our amount of B and A is going down, but our rate has to be positive, then we need a negative number or a negative sign. Every time 1 mole of B is consumed, 2 moles of A are consumed. Thus, the rate of A being consumed is twice the overall rate of the reaction. To make these equal, that means that we would need to multiply the rate of A that we observe by 1/2. Last but not least, this is equal to the rate of formation of our product. And in this case, the amount of product is going up with time. Since the amount of product is going up with time, this number does not need to be negative. Each of these is related to our rate law. Recall that that rate law has a rate law constant, and that rate law constant is temperature dependent. We saw previously in looking at the example with phenolphthalein and sodium hydroxide that when we raised the temperature, the reaction sped up. Temperature doesn't appear anywhere else in the equation that we're going to look at, so it must be in the rate law constant. We'll be looking at the role of temperature and the rate law constant a little bit later. We're then going to have our concentrations of our reactants, and each is going to have an exponent denoted by N and M in this case. N and M are the order of each of these reactants. These can have orders like 0th order, 1st order, or 2nd order. Those would correspond to values like 0, 1, or 2. Remember that rate laws, unlike equilibrium constant expressions, must be determined from experiments or advanced theory. They cannot be determined from only the chemical reaction equation. In the case of this particular example, these values might be something like 2 and 0. What does that mean, and how would we determine these? These orders for the rate law can be determined by looking at how a rate changes relative to concentration. For a given concentration change, what would we expect for the rate for a 0th, first, and second order process? Well, in the 0th order case, taking a number to the 0th power would turn it into 1. So in this case, if we were to double the concentration of a reactant that was present in the rate law to the 0th order, the rate would not change. In essence, we're multiplying by that 1. A compound that is present, but as a 0th order component, is often not written in the rate law at all. And this rate law that we wrote here as an example would more properly be shown without B present. That's because in this case, if B were 0th order, it would not be relevant to the rate law. But let's put B back in, and we'll imagine that it has some other order. A compound that is present with a first order value means that doubling the concentration should also cause the reaction rate to double. That one's pretty straightforward. Last but not least, a compound present at second order should cause the rate to quadruple. Remember, because these are experimentally determined rate laws, the actual experiment, changing the concentration and looking at the rate, must be conducted in order to determine this information. The overall order of the rate law is equal to the sum of all of our individual orders. So, in an example where A and B were each present perhaps at first order, the overall order would be second order.